Suppose we're interested in exam scores, which are normally distributed with a mean of 75% and a standard deviation of 10. In Chapter 6, we calculate the probability that a randomly picked exam will have a grade between 70 and 80%. In Chapter 7, we calculate the probability that the mean from a sample of 100 exams is between 70 and 80%. The distribution of the sample mean is taller and skinnier than the distribution of exam scores because the standard deviation is equal to 10 divided by the square root of sample size 100. In Chapter 8, we do not know the population mean or the population proportion. Hence, we need to compute the best and worst case scenarios for a population parameter, like the mean, using statistics like the sample mean and the sample standard deviation. The best and worst case scenarios of the population mean is called a confidence interval. The confidence interval probably contains the true value of the population mean. The population mean is either in this interval or it is not. Thus, the probability that it is in this interval is either 1 or 0. If the confidence interval was constructed with 95% confidence, we can say that we are 95% confident that the interval contains the population mean. A point estimator cannot be expected to provide the exact value of the population parameter. The probability that the sample mean equals the population mean is 0. An interval estimate can be computed by adding and subtracting a margin of error to and from the point estimate. The purpose of an interval estimate is to provide information about how close the point estimate is to the value of the parameter. In other words, the interval estimate provides a worst and best case scenario of, say, the population mean. The interval estimate of the population mean is equal to the sample mean plus or minus the margin of error. The margin of error is what we call a z-value times the standard error of the sample mean, or the z-value times the standard error of the sample mean, which is just the standard deviation of the population, divided by the square root of n. When sigma is known, we use z. When sigma is unknown, we use an estimate of sigma, and for that reason we use a t-value instead of z, where s is the sample standard deviation. The interval estimate of the population mean, mu, is x bar plus or minus the margin of error, which is the z-value times the standard error, or z-value times the population standard deviation divided by the square root of the sample size n. X bar, again, is the sample mean. 1 minus alpha is the confidence coefficient. Z subscript alpha divided by 2 is the z-value, providing an area of alpha divided by 2 in the upper tail of the standard normal probability distribution. Sigma is the population standard deviation, and n is the sample size. In Chapter 8, we have no idea what the population mean equals, but someone does. Your deity, for example, knows what the population mean is, but we mere humans don't have a clue what it is, and we're not going to know what it is in most cases. But it lies somewhere on the number line. On the other hand, suppose your deity reveals to you that the population standard deviation is equal to 10, and you randomly sample a population 64 times. For example, 64 randomly chosen people tell you their age. The standard error is thus equal to 10 divided by the square root of 64, which is 1.25. If your boss wants the interval estimate to provide her with 95% confidence, 1 minus 0.95 equals alpha of 0.05. Because there are two tails in every interval estimate, alpha is divided by 2, which equals 0.025. And because 0.025 is in row negative 1.9 and column 0.06, of the standard normal table, z equals 1.96. The margin of error is equal to the z value times the standard error, which equals 1.96 times 1.25, which equals 2.45. Suppose the first time you randomly sampled a population 64 times, it resulted in a mean age of 31.25. Thus, the first x bar is equal to 31.25. Notice that the first x bar is slightly above the population mean. In reality, you won't know this because your deity knows this. Only your deity knows this. The upper endpoint of the interval estimate equals x bar, 31.25, plus the margin of error, 2.45, which equals 33.7. The lower endpoint of the interval estimate equals x bar, 31.25, minus the margin of error, 2.45, which equals 28.8. The distribution of the sample mean is normal. Its standard deviation is equal to 1.25, and the confidence level is 0.95. It is centered at the sample mean of 31.25 because the population mean is unknown. Students oftentimes believe this means the probability of the population mean mu being between 28.8 and 33.7 is equal to 0.95. This is incorrect because the population mean is either in this interval or it is not. Thus, probably that the population mean is between 28.8 and 33.7 is either equal to 1 or 0, which only your deity knows. In this scenario, the population mean happens to be in the interval. This is the more likely scenario because you have estimated a 95% confidence interval. Suppose the second time you randomly sample the population 64 times results in a mean age of 28.15 years. This is the second x bar, and it is slightly below the population mean. Again, in reality, you won't know what the population mean is because only your deity knows this. The upper endpoint of the resulting interval estimate equals the second x bar, 28.15, plus the margin of error, which hasn't changed, 2.45. That sum is 30.6. The lower endpoint of this interval estimate equals the second x bar, 28.15, minus the margin of error, 2.45, which equals 25.7. The distribution of the sample mean is normal. Its standard deviation is still equal to 1.25, and the confidence level is 0.95. It is now centered at the sample mean of 28.15 because the population mean is unknown. The bell-shaped curve slides to the left until it's centered at the second population mean, or the second sample mean of 28.15. Again, students oftentimes believe this means the probability of the population mean mu being between 25.7 and 30.6 is equal to 0.95. Again, this is not correct because the population mean is either in this interval or it is not. Thus, the probability that the population mean is between 25.7 and 30.6 is either equal to 1 or 0, which, again, only your deity knows. In this scenario, the population mean happens to be in the interval. This is the more likely scenario, again, because you have estimated a 95% confidence interval. Suppose the third time you randomly sample the population 64 times, you get a sample mean age of 33.25 years. The third x bar is above the population mean. Again, in reality, you won't know this because only your deity knows this. The upper endpoint of the resulting interval estimate equals the third x bar, 33.25, plus the margin of error, 2.45, which again hasn't changed. That sum is 35.7 years. The lower end point of this interval, 30.8, is from subtracting the margin of error, 2.45, from x bar 3, 33.25. The distribution of the sample mean is normal. Its standard deviation is still equal to 1.25. The confidence level is still 0.95, and it is now centered at 33.25 because the population mean is unknown. The bell-shaped curve slides to the right until its center is located at 33.25. Again, students oftentimes believe this means the probability of the population mean being between 30.8 and 35.7 is equal to 0.95. Again, that is not correct because the population mean is either in this interval or it is not. Thus, the probability that the population mean is between 30.8 and 35.7 is equal to 1 or 0, which again, only your deity knows. In this scenario, the population mean isn't in the interval. So the probability the population mean is in this interval is 0. This is the less likely scenario because you have estimated a 95% confidence interval. Notice that the 2 of the 3 intervals contain mu. Again, you won't know this because only your deity knows this. Now, if we construct 997 more of these intervals, 950 or 95% of them will contain the population mean. This is why we call this a 95% confidence interval. In order to compute an interval estimate of the population mean, when the population standard deviation is known, the distribution of the sample mean needs to be normal. If the data from the population is normally distributed, a sample of any size can be used. If the data is from a population that is not normally distributed but is roughly symmetric, a sample size of 30 or more should be used. If the data is from a population that is heavily skewed or contains outliers, a sample size of 50 or more is recommended. Discount Sales has 260 retail outlets throughout the United States. The firm is evaluating potential location for a new outlet based in part on the mean annual income of the individuals in the marketing area of the new location. A sample size of 36 was taken. The sample mean income is $31,100. The population is not believed to be highly skewed. The population standard deviation is estimated to be $4,500, and the confidence coefficient to be used in the interval estimate is 0.95. Because 1 minus alpha equals 0.95, and there are 2 tails in an interval estimate, we need to find the values of negative z and z that correspond to left and right tail probabilities equal to alpha divided by 2, or 0.250. Because the population standard deviation is known, and we have a sample size of 36, and the population is not highly skewed, we can use the standard normal table. So we locate 0.0250 in the standard normal table, which is in row negative 1.9 and column 06. Because the probability that z is less than or equal to negative 1.96 equals 0.0250, and the normal distribution is symmetric, negative z equals negative 1.96, and z equals 1.96. Thus, plus or minus z subscript alpha divided by 2 is equal to 1.96. The margin of error is equal to z subscript alpha divided by 2 times the standard deviation of the sample mean, also known as the standard error of the mean, which equals 1.96 times the population standard deviation of 4,500 divided by the square root of 36, which equals 1470. Thus, at 95% confidence, the margin of error is 1470. And so the interval estimate of the population mean mu equals the sample mean of 31,100 plus or minus the margin of error of 1470, which corresponds to a lower endpoint of 29,630 and an upper endpoint of 32,570. We are 95% confident that this interval estimate contains the population mean mu because if we randomly sample the population, say, 1,000 times to construct 1,000 interval estimates, 950 of them, or 95% of them, will contain the population mean, mu. If an estimate of the population standard deviation, sigma, cannot be determined prior to sampling, we use the sample standard deviation, S, to estimate population standard deviation, sigma. This is the sigma unknown case. In this case, the interval estimate for the population mean mu is based on the t distribution. When sigma is known, we use z. When sigma is unknown, we use t because S, the standard deviation of the sample, is used as an estimate of population standard deviation, sigma. For now, we assume data from the population is normally distributed. The t-distribution is a family of similar probability distributions, all of which are symmetric and bell-shaped. A specific t-distribution depends on a parameter known as the degrees of freedom. In this chapter, degrees of freedom refers to the number of independent pieces of information that go into the computation of sample standard deviation, S. Recall from chapter 3 that the sample standard deviation, S, is computed using an estimate of population mean known as the sample mean. If the population mean was known and used to compute the standard deviation, S, we would divide the sum of square deviations by n, and the degrees of freedom would be n. However, since the standard deviation, S, is computed with sample mean x bar instead of population mean mu, we divide the sum of square deviations by n minus 1. So the degrees of freedom are n minus 1. As the degrees of freedom increases, because larger and larger samples are being used, the difference between the t-distribution and the standard normal distribution becomes smaller and smaller. Below is the graph of the standard normal probability distribution. The t-distribution with 10 degrees of freedom is shorter and wider. A graph that is shown in red. The t-distribution with 20 degrees of freedom is shorter and wider. The t-distribution with infinite many degrees of freedom, 101 or larger is considered infinite many, has the same shape as the standard normal probability distribution. For more than 100 degrees of freedom, standard normal z-values provide a good approximation to corresponding t-values. In fact, the final row of the t-distribution table, which is located in the appendix of most textbooks, is identified by the symbol of infinity in the degrees of freedom column. This row contains t-values. These t-values are the same as corresponding z-values. For example, notice a t-value of 1.96 has an upper tail probability of 0.0250. In the standard normal table, 0.0250 is in row negative 1.9 and column 06. Thus, for any given tail probability, t-values and z-values are identical when the degrees of freedom are equal to infinity. In our case, anything greater than or equal to 101. What are the t and z values corresponding to an upper tail probability of 0.0250? If the sample size is 11, the degrees of freedom equals 10. The value in the t-distribution table associated with an upper tail probability of 0.0250 is denoted t subscript 0.0250. The t-value is found in column 0.0250 and row 10, which is equal to 2.28. The probability that t is greater than 2.228 equals 0.0250 when the degrees of freedom is 10. If the sample size is 21, the degrees of freedom equals 20. The value in the t-distribution table associated with upper tail probability of 0.0250 is denoted t subscript 0.0250. The t-value is found in column 0.0250 and in row 20, which is 2.086. The probability that t is greater than 2.086 equals 0.0250 when the degrees of freedom is equal to 20. If the sample size is over 101, the degrees of freedom is considered infinitely large. The t-value in the t-distribution table associated with the upper tail probability of 0.0250 is denoted t subscript 0.0250. The t-value is found in column 0.0250 and in row infinity, which is 1.96. The probability that t is greater than 1.96 equals 0.0250 when the degrees of freedom is infinite. If sigma is known, the probability that z is greater than 1.96 equals 0.025 as well. The interval estimate when sigma is unknown is equal to the sample mean x bar plus or minus the estimated margin of error, which is the product of the t-value and the estimated standard error. Like before, 1 minus alpha is the confidence coefficient. Like the z subscript alpha divided by 2, t subscript alpha divided by 2 is the t-value providing an area of alpha divided by 2 in the upper tail of the t-distribution with n minus 1 degrees of freedom. Because the population standard deviation is unknown, we have to use sample standard deviation S instead. Suppose you have no idea what the population mean and standard deviation are, and you need a best and worst case scenario estimates of the population mean. You can only randomly sample the population to compute these estimates. After randomly sampling a population 64 times, for example, 64 randomly chosen people tell you how old they are, the sample standard deviation and sample mean are equal to 11.5 years and 31.25 years. The first estimated standard error is thus equal to 11.5 divided by the square root of 64, which is equal to 1.4375. If your boss wants the interval estimate to provide her with 95% confidence, 1 minus 0.95 equals an alpha of 0.05. Since there are 2 tails in every interval estimate, alpha is divided by 2, which equals 0.025. The t-value is found in row 63 and column 0.025. Thus, the t-value equals 1.998. The first estimated margin of error is equal to the t-value times, which is 1.998, times the estimated standard error, which is 1.4375. The first estimated margin of error equals 2.87. After putting the first sample mean of x bar, 3.125 on the number line, notice how close it is to the population mean. In reality, you won't know this. Only your deity knows how close the first x bar is to the population mean. The upper endpoint of this interval estimate equals x bar, 31.25, plus the estimated margin of error, 2.87, which equals 34.12. The lower endpoint of this interval equals x bar, 31.25, minus the margin of error, 2.87, which equals 28.38. The distribution has a standard deviation equal to the estimated standard error of 1.4375 and a mean of 31.25. The confidence level is 0.950. Again, students oftentimes believe this means the probability of population mean mu being between 28.38 and 34.12 is equal to 0.95. Again, this is incorrect because the population mean is either in this interval or it is not. Thus, probably that your population mean is between 28.38 and 34.12 is either equal to 1 or 0, which only your deity knows. In this scenario, the population mean is in the interval, so the probability that the population mean is in the interval equals 1. This is the more likely scenario because you have estimated a 95% confidence interval. Suppose the second time you randomly sample the population, 64 times. It results in a mean age of 28.15 years and a sample standard deviation of 12.5 years. The second X bar is slightly below the population mean. Again, in reality, you won't know this. Only your deity knows this. The second estimated standard error is equal to 12.5 divided by the square root of 64, which is 1.5625. The second estimated margin of error is equal to the t-value times the estimated standard error, which equals 1.998 times 1.5625, or 3.12. The upper endpoint of the second interval estimate equals the second X bar of 28.15 plus the second estimated margin of error, 3.12, which equals 31.27. The lower endpoint of this interval estimate equals the second X bar, 28.15, minus the second estimated margin of error, 3.12, which equals 25.03. The distribution has a standard deviation equal to the estimated standard error of 1.5625 and is centered at 28.15, the sample mean. Students oftentimes believe this means the probability of population mean mu being between 25.03 and 31.27 is equal to 0.95. Again, this is incorrect because the population mean is either in this interval or it is not. Thus, the probability that the population mean is between 25.03 and 31.27 is either equal to 1 or 0, which only your deity knows. In this scenario, the population mean happens to be in the interval, so the probability that the mean, mu, is in this interval equals 1. This is the more likely scenario because you have estimated a 95% confidence interval. Suppose the third time you randomly sample a population, the 64 times, the mean of the sample is 33.25 and the sample standard deviation is 11.1. The third sample mean is greater than the population mean. Again, in reality, you won't know this because only your deity knows this. The third estimated standard error is equal to 11.1 divided by the square root of 64, which is equal to 1.3875. The third estimated margin of error is equal to the t-value times the third estimated standard error, which equals 1.998 times 1.3875, or 2.77. The upper endpoint of this third interval estimate equals the third sample mean of 33.25 plus the third estimated margin error of 2.77, which equals 36.02. The lower endpoint of this interval estimate equals the third X bar of 33.25 minus the third estimated margin error of 2.77, which equals 30.48. The distribution is located at 33.25, the third sample mean, and standard deviation of 1.3875, which is the third estimated standard error of the mean. The true population mean, mu, is not in the interval 30.48 to 36.02. Remember, only your deity knows what the value of the population mean is. If we construct 997 more of these intervals, 950 of them, or 95% of them, will contain the population mean mu. This is why we are 95% confident that this particular interval estimate contains the population mean. A reporter for a student newspaper is writing an article on the cost of off-campus housing. A sample of 16 efficiency apartments within a half mile of campus resulted in a sample mean of $650 per month and a sample standard deviation of $55. Compute a 95% confidence interval estimate of the mean rent per month for the population of efficiency apartments within a half mile of campus. We will assume this population to be normally distributed. At 95% confidence, alpha is equal to 0.05. Because there are two tails in any interval estimate, we divide alpha by 2, which equals 0.025. The t-value is based on degrees of freedom equal to the sample size minus 1, which is equal to 16 minus 1, or 15. The t-value is in column 0.025 and row 15, which is 2.131. The interval estimate is equal to the sample mean plus or minus the estimated margin of error, which is the t-value times the estimated standard deviation, sample standard deviation, divided by the square root of the sample size. Recall the mean rent from the sample is $650. The t-value is equal to 2.131. The sample standard deviation is 55, and the sample size is 16. The interval estimate equals 650 plus or minus the estimated margin of error, 2930, or 620.70 to 679.30. The point estimate of the population mean mu is the mean rent from the sample. The interval estimate comprises two numbers, worst and best case scenarios. We are 95% confident that the mean rent per month for the population of efficiency apartments within a half mile of campus is between $620.70 and $679.30. The t-distribution can be used to estimate the interval estimate of the population mean mu when sigma is unknown and one of the following is true. The data is normally distributed and the sample size is bigger than 1. The data is roughly symmetric and the sample size is bigger than 15. The data is slightly skewed and the sample size is greater than or at least 30. The data is heavily skewed and the sample size is at least 50. If the population standard deviation is known, the margin of error used in the interval estimate of the population mean, mu, is computed with z-values from the standard normal table and the population standard deviation. If the population standard deviation is unknown, use sample standard deviation S to estimate the population standard deviation sigma. To estimate the margin of error in the interval of the population mean mu, also instead of using z-values, you must use t-values. We can reduce the margin of error by increasing the sample size, which reduces the standard error for a given level of confidence. Although arbitrarily choosing very large samples generates small margins of error and precise estimates of population means, unnecessary large samples are very expensive. On the other hand, small samples are associated with large margin of errors. The necessary sample size is not too big, not too small, but just right, which is found by solving the margin of error for sample size n. Let E denote the desired margin of error, which is the amount that is added to and subtracted from the point estimate to obtain an interval estimate of the population mean mu. The equation for the margin of error is equal to z times sigma divided by the square root of n. Solving this equation for sample size n yields a necessary sample size equal to your z-value squared times your population variance divided by the desired margin of error. Recall the discount sounds is evaluating a potential location for a new retail outlet based in part on the mean annual income of the individuals in the marketing area of the new location. Suppose that Discount Sounds management team wants an estimate of the population mean such that there is a 95% probability that the margin of error is 500 or less. How large should the sample be to meet the required precision? Recall the population standard deviation is equal to $4,500. In this example, we could set the desired margin of error of $500 equal to the margin of error, which is z times the standard deviation of the population divided by the square root of n, the sample size. And then solve this for n after we plugged in values for z and sigma. Instead, we're going to use the shortcut necessary sample size equation that we just derived. At 95% confidence, alpha is equal to 0.05. Alpha divided by 2 is 0.025. And so z is equal to 1.96. In this example, the population standard deviation was equal to 4,500. Plugging these values into the equation for the necessary sample size yields 1.96 squared times 4,500 squared divided by 500 squared, which equals 311.17. Since this is not an integer, the necessary sample size is 312. A sample size of 312 is needed to reach a desired precision of plus or minus 500 at 95% confidence. If we use a sample size of 311 or smaller, the margin of error will be more than $500 at 95% confidence. The general form of an interval estimate of the population proportion is sample proportion plus or minus the margin of error. The distribution of the sample proportion plays a key role in computing the margin of error for this interval estimate. Recall in Chapter 7 that the distribution of the sample proportion can be approximated by a normal distribution whenever the sample size times population proportion p is at least 5, and the sample size n times the quantity of 1 minus the population proportion is at least 5. However, in Chapter 8, we do not know the population proportion p, so we have to use the sample proportion p bar. An interval estimate of the population proportion p is sample proportion p bar plus or minus the margin of error, which is the z value, times the square root of p bar times 1 minus p bar divided by the square root of sample size n. Recall from the previous video that the numerator of the margin of error here is just the standard deviation of the dummy variable that was equal to 0 and 1 for two different scenarios. 1 minus alpha is the confidence coefficient. Z alpha divided by 2 is the z value providing an area of alpha divided by 2 in the upper tail of the standard normal probability distribution. P bar is the sample proportion, which is known as the point estimator of the population proportion. Political Science Incorporated, PSI, specializes in voter polls and surveys designed to keep political office seekers informed of their position in a race. Using telephone surveys, PSI interviewers ask registered voters who they would vote for if the election were held today. In a current election campaign, PSI just found that 220 registered voters out of 500 contacted favor McSame. PSI wants to develop a 95% confidence interval for the proportion of the population of registered voters who favor McSame. Sample proportion P bar is found by dividing 220 by 500, which is 0.44. Also, since the confidence level is 0.95, alpha is 0.05, alpha divided by 2 is 0.025, and the z value is 1.96 because 0.025 is in row negative 1.9 and column 0.06 of the standard normal table. The interval estimate of the population proportion P is found by substituting sample size 500, sample proportion P bar 0.44, and Z equal to 1.96 into the expression These values are the sample proportion. This value is the z-value, which provides an area of 0.025 in the upper tail of the standard normal probability distribution. And this is a sample size. The interval estimate is equal to 0.44 plus or minus 0.0435. Thus, PSI is 95% confident that the proportion of voters that favor McSame is between 0.3965 and 0.4835. If the upper limit of this confidence interval was larger than 0.50, the race between two political candidates is considered a dead heat. For a given level of confidence, the margin of error, E, can be reduced by increasing the sample size because this reduces the standard error. Although arbitrarily choosing very large sample sizes generates small margins of error and precise estimates of the population proportions, unnecessary large samples are very expensive. On the other hand, small samples are associated with large margin of errors. The necessary sample size is not too big, not too small, but just right. If we let E denote the desired margin of error, we can solve this for n. The resulting equation is z squared times p bar times 1 minus p bar divided by the desired margin of error squared. Because sample proportion p bar will not be known until after we have selected the sample, we use a planning value of p star instead. The necessary sample size is thus n equal to z squared times p star times 1 minus p star divided by the square of the desired margin of error. If this value is not an integer, round it up to the next higher integer. Planning value p star can be chosen by 1. Using the sample proportion from a previous sample of the same or similar units, or 2. Select a preliminary sample to compute a preliminary sample proportion, or 3. If no information is available about the population proportion. 0.5 is often assumed because it provides the highest possible sample size. Suppose that PSI would like a 0.99 probability that the sample proportion is within 0.03 of the population proportion. How large should the sample be to meet the required precision? Recall that in the previous example, a sample of 500 similar units yielded a sample proportion of 0.44. This is our p star. In this example, we could set the desired margin of error to 0.03 and then solve this for n. This is unnecessary since we have an equation for the necessary sample size. At 99% confidence, alpha is equal to 0.01. Alpha divided by 2 is 0.005. So z is equal to 2.575. In this example, preliminary proportion p star is equal to 0.44. This was from our previous PSI example. Plugging these values into the equation for the necessary sample size yields 0.2575 squared times 0.44 times 0.56 divided by 0.03 squared, which when rounded up equals 1816. A sample size of 1816 is needed to reach a desired precision of plus or minus 0.03 at 99% confidence. If we use a sample size of 815 or smaller, the margin of error will be larger than 0.03 at 99% confidence.